Okay, everyone, welcome to the first live session today, Science of Earthquakes, with Dr. Wendy Bohon by Learning Geology. Learning Geology is a community organization that aims to promote geoscience literacy worldwide. Today's session is one of the 7 geoscience outreach session, which is part of Sustained Geoscience Outreach Project. These live sessions are presented by top experts in geoscience field. These are open to everyone, open to all backgrounds and ages. No prior experience is needed. You can register and you can find more details on the link shown on the website screen. In today's live session, a bit before I start this session, I would like to introduce Dr. Wendy Bohon. She's an earthquake geologist and science communication specialist. She's also AAS ambassador. Dr. Wendy Bohon has worked on different seismology and science communication projects in the past. She has worked with USGS, IRIS, and recently with NASA. Myself, I'm a co-founder at Learning Geology, and I'm also a PhD student at University of Prince Edward Island in Canada. In today's session, Dr. Wendy will share that why earthquakes happened, what can we do about it. We will explore some causes and impacts of earthquakes with Dr. Wendy Bohon. With this, I would like to pass to Dr. Wendy Bohon.
Hi, thank you. I'm going to share my screen. All right. You'll get to see a preview of what's coming before I put it on. We are a little bit ahead of the hour, so I'll just take this time to thank Learning Geology for having me. I do think it's really important that we talk to people about geoscience and why it matters, because we don't always make the connections about how what we study actually impacts people. And I know that a lot of folks, especially if they're just starting out in their career, want to make a difference in the world. They want a job that's going to be able to, pay the bills, but also that's going to make a difference in the world, that's going to be something that they enjoy, that's going to be something that's challenging and interesting. And I think geoscience is one of those fields where there's a lot of room to grow, and there's a lot of room to explore, not just explore the world, but also explore the things that you like to do and learn a lot of new skills. So there's always new stuff to be learning, especially in the field of earthquakes, which is what I'm going to talk to you about today. So we are right at the top of the hour. Thank you, everyone, for joining. I hope everybody can hear me, and feel free to ask any questions, and we will answer those at the end, if that's okay, just so I'm a little bit sick, so I'm trying to keep my train of thought. So I'm going to talk to you today about the science of earthquakes. So science is fundamentally about asking questions. And the questions that I find myself often asking as an earthquake geologist are, where are the faults? How often are there earthquakes on those faults? How big are those earthquakes? When might the next earthquake likely occur? And what effect would those earthquakes have on people and infrastructure, or the built human environment? And so we'll walk through some of these questions and how we go about finding the answers. But first, we have to start every story at the beginning. So it's really important to have a big picture idea of why earthquakes happen in the first place. And to understand that, we have to understand the very basic composition of the Earth. So most of the Earth is made up of the mantle. That's about 67% of Earth's mass. The part that we live on, the rocky exterior, is called the crust, and that makes up less than 1% of the Earth's mass. It's kind of like the shell of a hard-boiled egg. And rather like the shell of a hard-boiled egg, if you crack it, the crust is broken. It's broken up into these big pieces that we call tectonic plates. So each one of these different colors is a different tectonic plate. And these are moving around very slowly. The places where these tectonic plates come together and touch each other, the places where we have the most earthquakes. So each one of these flashes of light is an earthquake. And there are hundreds of thousands of earthquakes every year around the world. Look at all those quakes. So there are different ways that the plates can come together. They can slide past each other. We call this a transform boundary, and these kinds of boundaries have strike-slip faults. So the San Andreas fault is a strike-slip fault. The plates can pull away from each other. This is called a divergent boundary. This is what's happening in the mid-ocean ridge, where new crust is being born. The plates are pulling apart. But you can have continental crust that pulls apart too. And we're going to talk a little bit about the basin and range where the continental crust is extending. There are also places where the plates come together, and this is called a convergent boundary or a convergent margin. And this is where you get subduction, where one plate is pushing down underneath another plate. In these areas, we get compression, and this is where you get things called thrust faulting. So faults are where earthquakes happen. And so it's really important that we find the location of faults around the world, because the places where the faults are the places where the earthquakes are going to be. So how do we find the faults? We can go about doing that in lots of different ways. One of those is using geophysical instruments. So the instrument that you see on the right is a GPS station or a GNSS station, depending on where you are. And this is the same sort of thing that we have in our phone or in our car, but it's a much more high-tech, sophisticated, and precise instrument. So this can measure how the crust is moving in very, very small increments and in any direction. And so we have hundreds of these around the country, thousands of them around the world, and they're measuring these very small motions of the crust. So if you look at the map on the left, this is a map. You can't see the dots, but they're at the end of every arrow. Every one of those little arrows is basically a GPS station, and the arrow direction is showing the direction that the ground is moving, and the length of the arrow is showing you how quickly it's moving. And so you can see there are parts that are moving in completely different directions and at completely different speeds. And so we know if we have two GPS stations that are next to each other, but they're moving in different directions or at different speeds, something is happening to the crust in between those stations. It could be that the rocks are bending and stretching, but often what's happening is that there is a fault in between those. Here's an example of that. So here we have two GPS stations, and in this area, the crust is stretching. So one GPS station is moving away from the other one. This is what's happening in the Basin and Range province of the United States. This is the area in between the Sierra Nevada mountains and the Colorado Plateau. And we'll play that little animation again. What's happening as it stretches is that you have these faults that are forming, and that's what's causing the basins, the drop down parts, and the ranges, which are the raised up parts. And those are normal faults on either side. And because we know that those stations are moving, we would know that we want to go and look for faults in between those two stations. So one way we can go and find those faults is using this really cool technology called LiDAR. It stands for light detection and ranging. And you can put these instruments in planes, drones, helicopters. You can even have them on the ground. And the idea is that you know exactly, in this case, where the plane is, so you know where the instrument is, and you have a GPS unit on the ground, so you know exactly where it is in space. And there's a laser that scans back and forth across the ground, and all of those little hits of the laser bounce down to the ground and then come back up to the plane. And that makes a three-dimensional map of the surface of the ground. But the laser is really cool. It's thousands of pulses per second. And so it's almost like sunlight if you have trees or grass, where it filters through. Some of it will hit the top of the tree, some will hit some leaves and branches, but some will make it all the way to the ground. So the one that takes the longest to get back to the plane was the furthest away. So we know that was when the laser hit the ground. And this is important for finding faults in areas where there may be trees, like this area right here. So this is a LiDAR image of Northern California, and the San Andreas Fault cuts through this image. I want to orient you to what you're looking at. So the stuff that looks rough, like popcorn, those are trees. You can see what looks like a little sort of snake running through here. That's a road. There's a square in the bottom left-hand corner. That's a fence. So a lot of human elements in this landscape that we can see. But we know the fault is here, but where is it? It's underneath all these trees. Because we have the LiDAR, and because the LiDAR, the laser light filters through the trees, sort of like sunlight, we can take those very last returns that take the longest amount of time to get back to the plane and only keep those, which means we can get rid of all of these pesky trees, which allows us to see the surface of the ground. And we can interpret clues in the surface of the ground to figure out exactly where the San Andreas Fault is in this area. Don't worry, we can put the trees back. And this is actually a useful thing for biology as well, because it can tell you something about forest health. It tells you about the canopy height and the tree density and those sorts of things. So why do we want to know exactly where the fault is? There's a couple of reasons, but one of those is that if we know where the fault is, then we can learn a lot about the earthquake history of the area doing something called paleoseismology. So paleo is ancient, seismology is earthquakes. So this is the study of ancient earthquakes. And in this case, we dig down across an active fault and we look at the layers that are exposed. So when an earthquake breaks the rocks, it leaves clues in the ground, and we can interpret those clues to figure out how many earthquakes occurred in this particular spot through time. So this is the sort of thing we're looking at on the walls of that trench, the hole that we dug. Obviously, it doesn't have the colors and stuff. We go through and we make very careful mapping and observations of the layers that we see. So when you have sedimentary layers, they're laid down generally horizontally or flat. It's called the law of original horizontality. If they're no longer flat or if they've been moved, that means something happened. And in this case, it's earthquakes. So the red line that you're seeing is the fault that comes up. Now, if we follow the layers across, like this purple layer, you can see that it ends and it goes down there. And again, these are just marking off things that we would see in the field. This one right here is a good one to look at. You can see that it's sort of a little bit lighter color rock. And then that stops at the fault and you can follow it down over here. All of these are clues about past earthquakes. We can see that in certain places, multiple earthquakes have happened. And if we can do things like carbon-14 dating on these different layers of rock that have been disturbed, we can figure out when these earthquakes occurred. If there's multiple earthquakes that we can see evidence for, we can figure out about how often those earthquakes occurred. That's called the recurrence interval. So now we have an idea of about how often this area would have earthquakes on this fault. So that's a really important clue. It's a hint about what the seismicity in that area is like through time. Because in geology, the past is the key to the future. If we can understand what happened in the past, we can have a good idea of what might happen in the future coming up. But this doesn't tell us about the magnitude or the size of the earthquakes. In order to do that, we need lots of paleoseismic trenches along faults. So this is showing Southern California. This right here is the San Andreas Fault going down just north of the the Salton Sea. And then the San Jacinto Fault is down here. All of these are helping to take up the motion between the North American Plate and the Pacific Plate. So why do we need all of these different paleoseismic trenches to figure out magnitude? How could we do that? So the magnitude of an earthquake, or the amount of energy that's released, is dependent in part upon the amount of fault that breaks during the earthquake. So the whole fault doesn't break in every earthquake. If a little section breaks, it would be a smaller magnitude. If the whole shebang breaks, it's going to be a really big earthquake. So we look for evidence of earthquakes that happened at the same time in these different trenches. If we only see an earthquake in a few trenches, maybe that means that was a smaller earthquake. If we see it in all of the trenches, then we know that was a much larger magnitude earthquake. So now we have an idea of how often earthquakes happen in this area, and we can get an idea of how big they are. But I haven't actually defined for you what an earthquake is. Now, everybody comes into this with an idea of what it is, right? You think it's usually what people think of as the shaking that comes with it, but an earthquake is actually the breaking of the rocks. So what's happening, you have the motion of the tectonic plates, and that's putting a lot of stress and strain on the rocks in the crust as they're moving because they're stuck together. Eventually, that stress is going to build up so much that it breaks the rocks. And when it breaks the rocks, it sends out energy in all directions. That energy is what we feel as shaking. And so when most people think of earthquakes, what they think of is ground shaking. We're going to look at some ground shaking in this video. This is a market in central Kathmandu in Nepal. And in 2015, they had a devastating magnitude 7.8 earthquake. Two things I want you to watch here. The first, if you look at the square that's inset, this is showing a nearby GPS unit. Remember, we were talking about how that shows the motion of the crust. I want you to watch how the GPS unit is reflecting what the people are feeling in this market as the earthquake is happening. So it's pretty spectacular, right? The ground is actually moving in ways that we don't often think about. Usually you think about it jolting up and down, but it can have these big side to side motions. There's all different ways that the ground moves during earthquakes. But what you feel in any location may be different due to several different factors. guess we can watch this again since apparently my computer wants to show it to you again. So we've already talked about one of those factors, right? The magnitude of the earthquake or the size of the earthquake. That's about the amount of energy that's released. Every earthquake has one magnitude, but it generates many different levels or intensities of seismic shaking, ground shaking. The map that you're looking at over here is a map showing the amount of shaking that was experienced across the area during the Ridgecrest earthquake in California in 2019. This was a magnitude 7.1. The epicenter of the earthquake is this star right here. So earthquakes don't actually happen at the epicenter. They actually happen at the hypocenter, which is a point deep inside the earth. The epicenter is the point on the surface directly above that. Just a little nomenclature for you. The areas in red are the areas that experienced violent or extreme shaking. Then the areas in orange and yellow were strong to very strong shaking. And then the greens and blues were light to weak shaking. And for the most part, you can see that the strongest shaking was right around the epicenter. But if you look over here, there was also really severe violent shaking kind of a little bit further away. And then you had some sort of moderate shaking in the middle. And if you look carefully, you can see in these valleys, these flat areas, the shaking in these areas was strong, but it's separated by areas of moderate to light shaking. Well, why is that? That's because of the local rock and soil conditions. So seismic waves, when they're traveling through bedrock, they just travel right through and keep on going. But when they're in soft sands and soils, like the kinds of sands and soils that are in valleys, they get stuck. It's called amplification. So you will actually shake harder and for a longer period of time if you're on these soft sands and soils. Additionally, your distance away from the earthquake matters. And that intuitively makes sense because, if you're close by to where the earthquake happens, you would expect that you would feel stronger shaking. And as you move away, generally speaking, you're going to feel less shaking. But we're looking at a map and thinking about driving distance, right? Your distance from the earthquake also matters in terms of what you see, how far it is inside of the earth away from you. So not just your horizontal distance away, but also your vertical distance away. So as I said, earthquakes start at a hypocenter. That's the point deep inside the earth. Sometimes the hypocenter can be deep, like it was in the Hindu Kush earthquake. That was just over 200 kilometers deep, whereas in the Kashmir earthquake in the same general area, same magnitude earthquake, it was only 23 kilometers deep. So in this little clip, we're going to look at the difference that made for shaking on the surface. So for the Hindu Kush earthquake, again, it was a magnitude 7.5. There were areas of light to moderate shaking, unfortunately 400 fatalities. With the Kashmir earthquake, only 23 kilometers, there were quite a few more casualties, 87,000 folks, but we had really violent and severe shaking near the epicenter. So your distance away from the earthquake makes a great deal of distance, both the horizontal distance and the vertical distance. If you have shallow earthquakes in particular, you can also have another effect of earthquakes. Not every earthquake breaks the surface of the ground. And when it does, we call that ground rupture. Ground rupture can be problematic for lots of reasons, partially because if it goes underneath the building, it can tear the building in half. And you can see that here. This was from the Kaikoura earthquake in New Zealand. This little cottage got ripped apart. After the 1971 Silmar earthquake in California, they instituted some laws, one of which was called the Alquist Priolo Zoning Act, which said that you can't build structures across an active fault. You have to be at least 50 feet away from the active fault so that this exact thing doesn't happen. Another thing that can happen that we don't often think of with earthquakes is something called liquefaction. Now, many of us have experienced liquefaction in our lives. Have you ever stood on the edge of the seashore or on the edge of a lake in like the soft sandy soil or the mud, and you wiggle your feet or you wiggle your toes or you stomp and you sort of sink down into the ground? That's liquefaction. And if you have an area with soft sand and soil and a high water table and earthquake waves come through, the exact same thing will happen. What's happening there is that as the waves come through, they force water up. That pushes all those little sand and dirt grains apart and causes the surface to lose strength. So here's a video demonstrating how that works. So you don't actually sink in like quicksand, but it does cause the ground to lose strength in such a way that it can be really, really damaging for structures and other heavy objects that are on the ground in that area. This was a real problem during the San Francisco earthquake in 1906, especially in the Marina District. Landslides are another huge hazard from earthquakes. This is an image from the Pacific Palisades after the Northridge earthquake. And after Northridge, there were more than 9,000 earthquakes around the Los Angeles area. These are especially prevalent, obviously, in hilly areas, but in any place where you have had fires recently, because the vegetation roots actually help to hold the ground. They keep the stability of the ground. And if those go away, now you've lost the stability of the ground. Additionally, if you have construction or other things that have kind of disturbed the area, you're at a higher risk for landslides. So this is a map from the California Geological Survey, and it's showing different earthquake hazards in one particular area. So Pacific Palisades is up here. I used to live, where was it? Right over here somewhere. I was kind of in the Hollywood Hills area, but down here is Santa Monica for folks that are familiar with the area. Here's UCLA. So these are different seismic hazards. The whole area has earthquake shaking hazard. This area in green is areas that can experience liquefaction during earthquake shaking. In fact, if you look carefully at the map, there's a road called La Cienega that goes through this area. And in Spanish, La Cienega means the swamp. So this was a swampy area before LA turned into this giant city. The areas that are yellow that have the dotted line in the middle, these are areas that have had previous ground rupture. So these are places where the faults have broken the surface. So we have to be careful there of building in these particular areas because that could be really damaging to the buildings. And up here, this light blue, these are landslide areas that have a high landslide hazard. These are the hilly areas. Malibu is over this way. So lots of different kinds of hazards in this same map. And that brings up a really important point. When we talk about hazards, earthquakes, or any kind of hazards, we talk about the hazard versus the risk. And these are two concepts that are very similar and they're related, but they're not the same. And I like to think of them talking about sharks. So a hazard is something that has the potential to harm you, like a shark in the water. Risk is the likelihood of that hazard causing harm to you. So if you're on the shore and the shark is in the water, the hazard is still there, but your risk is very low. If you get into the water, the hazard is there, and now your risk has gone up. So hazard and risk related, but not the same. All right, so now we know why earthquakes occur. We know generally where they happen. Earthquakes occur because of the motion of the tectonic plates. They happen in places on faults, but generally where the tectonic plates are coming together. We know about how big they can be because we do paleoseismology and look at instances of past earthquakes to figure that out. And we know what areas are most vulnerable because we can map out different hazards like landslides and like liquefaction in areas that will shake the most because of their local soil conditions. What we don't know is when exactly the earthquake will happen. Because like I said, talking about paleoseismology, we get an idea of the recurrence interval, but this is over geologic timescales. So this is plus or minus 100 years, plus or minus 200 years. And when you're thinking about predicting earthquakes, that's not what people want to hear. They want to hear we're going to have a magnitude 7 Friday at 2 or something like that, right? It doesn't work that way, partially because we don't know what exactly is going to be the thing that causes that fault to break. We know stress and strain is building up in the crust, and we know how much because of those GPS instruments, right? But we don't know exactly what the point of failure will be. So what we do instead of predicting is something called forecasting. And it's very much like weather forecasting over much longer timescales. So instead of saying there's a 60% chance of rain tomorrow at noon, we say there is a 67% chance of a magnitude 6.7 or greater earthquake in the Los Angeles area in the next 30 years. So why 30 years? Because that's kind of the longest time frame that human beings think over. That's the length of most mortgages. So we're used to thinking in time frames of about that long. And so we're trying to give people an idea of what they can expect in their lifetime. Because if we know what's coming and know what to expect, then we can build to withstand that shaking. We can make sure that our schools and our buildings and our roads are going to be able to withstand the types of earthquakes that have happened before. And, does it really matter if we know if they're coming next week, next year, 10 years? I mean, of course, but what we should be doing is making sure that we are resilient to that hazard before it happens. So what are some things that we can do to make sure that we are resilient to earthquake hazards? So this is the 7 steps to earthquake safety. You can find more information from this from the Earthquake Country Alliance. The first thing you want to do if you live in earthquake country is make sure that you have the interior of your home safe. You want to strap down bookcases, anything that could fall on you, large pieces of furniture, strap down your water heater. Step 2 is to make a plan. Sit down with your family. Make sure that they know what to do if they're at school when an earthquake happens, if you're at work when an earthquake happens. Make sure you know what to do if you're in a tsunami evacuation zone, those sorts of things. Step 3, make sure you get together your emergency kit. And these emergency kits are good for just about everything. It could be fires, snowstorms, hurricanes, earthquakes. It's the same basic thing. You want to have at least 2 weeks of food and water. You want to have extra medication. Don't forget your pets. They're part of the family. They need extra food and water, flashlights, batteries, medical supplies, important documents. All of those things would go into your emergency kit. The next step would be to secure your space structurally. So make sure that your home is bolted to the foundation. Make sure that you have shear walls to help protect your home from that side to side shaking. And then this step down here is one that we all need to think about because almost everywhere can experience earthquake shaking. You don't have to be along an active plate boundary because there are earthquakes in other places. They just happen less frequently. So if you feel earthquake shaking and you live in the United States, the recommended action is to drop down to the ground, take cover underneath a sturdy object like a table, and then hold on tight until all shaking has stopped. If you live near the coast in a tsunami hazard zone and you experience prolonged earthquake shaking, that could be your natural tsunami warning. So that's when you would want to put your tsunami action plan into place. Wait until shaking has stopped and then evacuate along your tsunami route. After all of the shaking has stopped, what you want to do is clean up, make sure that you are getting rid of any hazardous materials, any broken glass, any chemical spills, help people that are injured, check on your neighbors. And then finally, we want to rebuild. And that's the important thing that we need to think about. Earthquakes are going to happen. There's nothing we can do to stop them. And we don't just want to survive the earthquake. We want to thrive in the aftermath. So we have to make sure that we're prepared for them when they happen, that our buildings, our homes, our structures can be used after the earthquake because it's not just enough to survive, right? We want to thrive. So if you have any additional questions, we're going to have plenty of time for question and answer. But if you have any additional questions, feel free to reach out to me on social media. I'm Dr. Wendy Rocks, except on TikTok. Somebody already had that name, so I'm Dr. Wendy Rocks it. So I will stop screen sharing now. Oh, this picture, I did my PhD work in the Himalayas on the border between India and Pakistan. And this is the sign that is on the border between India and Pakistan there. Without geography, you're nowhere. It's a very odd place to come across a Jimmy Buffett quote, but there you have it. All right. Did we have any questions?
Thank you so much, Wendy, for an amazing session with so many informative infographics, animations. Yeah, we do have one question and a couple of general comments. So one question is from Natalie N. She has asked, like, I have read and seen in documentaries that New Madrid fault was a failed rift, but also it could be from isostatic rebounding from the retreat of the ice sheets at the end of the last ice age. Have we formed a more definitive cause of this fault seismic zone? And is earthquake occurrence increasing, decreasing, or staying the same in the region? Is the nearby Wabash Valley seismic zone of same or similar origin?
Yeah, so the real foot rift, which is basically the New Madrid seismic zone, is it is a failed third rift. We know that's what it was. So a failed third rift, for those who are not aware, and there's no reason anybody should be if you're not a geologist. So I know you're a geologist asking that question. When you have a mantle plume that comes up, you break the earth in different ways. This is happening right now in Africa, right? You have two areas opening up that have water, and then you have a third rift down here that doesn't have water. That's the East African Rift Zone. The same thing happened in the United States, but the third arm of the rift that was, as the crust was sort of breaking apart and basically creating a new ocean, was where the Mississippi River comes down. And many of the world's great rivers flow along these failed third arms, these locogens. And so that's what the real foot rift came from. One of the reasons that they think it's still seismically active as it is today is because of the isostatic rebound from the glaciers. So when glaciers push down or ice sheets push down on the crust, that's a lot of weight. And so when you melt them, which happens very quickly, geologically speaking, it takes the time to spring back up. And anytime you're moving rocks around, they're going to be cracking and breaking, and that's earthquakes. You can kind of think about isostatic rebound like if you punch down pizza dough or some kind of dough, eventually it'll come back up, but it's kind of slow. It's sort of like that. And so the earthquakes that happen in the central and sort of Midwest are called intraplate earthquakes because they're not along the edge of the tectonic plate boundary, which is where most earthquakes happen. And in the United States, that's along the West Coast. So there are lots of faults, old breaks in the crust from past mountain building events. You know, we've had lots of different supercontinents. They slam together, they pull apart. There's been a lot of action on Earth, and we still have the records of those left over. And so those are weaknesses in the crust. The real foot rift, the New Madrid seismic zone, is one of those. And most of the other zones around there are at least related to that same set of processes. Are earthquakes there increasing? No. There are more earthquakes in parts of the United States than there ever have been before, but that is from a different process that we are doing. But that's not so much the case in the New Madrid area.
Thank you. So Natalie just said that, no, I'm just someone trying to get into seismology.
Oh, well, you're doing a great job. That's not like the normal thing. If you like mention it at a party, people are like, yes, exactly. Failed third rift. I mean, you could come to my parties because we talk about that, but.
Yeah, we have a total of more questions. Geo Hassan Nasir has asked, like, any new information about 6 February earthquake?
About which earthquake?
About 6 February earthquake, I think.
Oh, yeah, the Turkey earthquake.
Yeah.
I guess it depends on what you mean by new information. There's always, we're going to be learning about those quakes for decades. All the data is still being processed, and not just the seismic data, but also how the ground moved, exactly where it moved the most, how the faults ruptured. It was a very complex sequence of earthquakes. So it started on the northern part of the Dead Sea Fault, ruptured up to a different fault, and then actually went bilaterally. So earthquakes can rupture in one direction down a fault, they can rupture in another direction down a fault, or they can rupture in two directions at once. So it did that. It ruptured up, hit this other fault, and then it ruptured in two directions. And then, of course, the earthquakes change the stress in the crust nearby. And that causes both aftershocks and other earthquakes that can be significantly problematic, which are really just larger aftershocks. But that was what the magnitude 7.5 was. It was on a different fault system, but it was within the area that had stress change because of that set of earthquakes. So it was unlikely that that earthquake would have occurred at that time had the first earthquake not happened. But it was a very complex set of earthquakes, and some of the shaking patterns were really unexpected. But those earthquakes themselves were not unexpected, geologically speaking. So if you look at a map of Turkey, you can see that there are these areas of bright red that follow the North Anatolian Fault, the East Anatolian Fault, the Dead Sea Fault, a lot of these other faults in the area. Geologists knew that this was a hazardous area. There have been damaging earthquakes here historically. There have been damaging earthquakes here in antiquity. We know that this is a seismically active area. Most of the earthquakes that have happened historically in that area have not been quite that large, but they have been really, really damaging. So Was it surprising? No. Was the amount of damage surprising? Yes.
Yeah, so we have a couple of more questions. The next question is, what was the most impressive paleo earthquake that has been discovered?
The most impressive earthquake? Ooh.
Most impressive paleo earthquake that has been discovered.
That's a tough one. I think the coolest one that's ever been, and it wasn't done necessarily with paleoseismology, it was basically the last great Cascadia earthquake. And it's cool because it took all these different people using all these different methods to figure out what had happened. And so along the coast of sort of Oregon, Northern California, and Washington, there are these dead trees everywhere, red cypress. And these scientists, Brian Atwater, David Yamaguchi, I think that's his name. Oh my gosh, he's like a seminal scientist. I can't believe I've forgotten his name. I'm going to call it the cold medicine. But they were looking at why these trees had died. And they were looking at the soils in these areas. And they were like, why is this sand layer here? This looks like a tsunami deposit. That's strange. What if it's a tsunami deposit? And they wrote up that, they thought maybe there had been a tsunami here that had killed these forests. They're called ghost forests. And basically they get salt water. The trees get salt water around their feet because they drop down after the earthquake and then they die. And so they put that out into the scientific literature and it sort of was out there for a while. And then there was a scientist in Japan who was looking and he was like, there was a tsunami here. It's in the samurai records because in Japan, the records are really meticulously kept. And so they figured out that an earthquake happened along Cascadia in about 1700, because that's when they could tell that the trees had died. And then the samurai records said that it was, not only was it 1700, it was January 26th at 9 p.m. because they knew how long it took for the tsunami to cross the Pacific Ocean. And so by putting together records from either side of the Pacific, they were able to determine that there was this enormous magnitude earthquake along the coast of the Pacific Northwest that nobody knew about before. And so now, of course, we know that the Cascadia subduction zone is there, that it's this huge hazard, that it's something that we need to prepare for. And that was just in the 80s. I mean, it wasn't that long ago. So there's still big discoveries that are being made.
So another question for the same from the same person. How can you distinguish between earthquakes and ground movement from meteorite impact? Thinking about Yucatan Peninsula.
So meteorite impacts leave other kinds of clues. They have ejecta that come out. They leave a trace in the landscape, and they don't happen very often. And so earthquakes, there's hundreds of thousands of them happening all the time. And if we were to see things like sand boils or fissures or these other types of liquefaction features that could happen during earthquakes or during meteorite impacts, if there's faults nearby, it's sort of the Occam's razor situation where you're like, it's most likely that this was due to faulting, but you can see some things like that around meteorites. And I mean, they leave a significant record.
So we are just approaching to the close end of the time of the session. So we'll take this one more question. So I have a question. What would be the good advice to developing countries to outstand earthquakes, considering that sometimes the lack of technology or resources to build proper earthquake resistant structure is not enough?
It's terribly difficult to offer advice because people's situations are also different. Different countries are dealing with lots of different kinds of issues, not just geologic hazards, but the effects of climate change that they may have for instance, Haiti. There's hurricanes that come through there every year. And while they also have devastating earthquakes, those don't happen every year. So what do you build for? What do you prepare for? Do you have limited resources? And so I think part of it is being able to develop better technology, cheaper technology, better building practices that are going to be able to be implemented in places that don't have the resources. I think technology is going to take us a large part of the way. And I think we need to come together as a global community to address a lot of these issues, not just with earthquake hazards, but with the impending, hazard multiplier that is climate change. We really are going to have to work together to sort of ensure everyone's safety as we move forward, because disasters discriminate. And the people that are the most vulnerable to all types of hazards are usually the ones that are least able to prepare, respond, and recover. And we need to, as a human species, take care of our vulnerable. That's one of the things that makes us human, right? Is that we care for each other. So
we have more questions, but I think we have we are now at the end of the session today. Thank you everyone for joining. Special thanks to Dr. Wendy for joining us today and giving us this incredible presentation. We will be sharing the recording of this session on our Facebook and YouTube channel. Please join us for the upcoming sessions. These are for you to enhance your geoscience literacy by top experts in the geoscience field. Thank you again, everyone, and we wish you a great time of your rest of the day. Thank you.
Thanks for having me. And all the speakers are going to be great, but Denali is going to be extra awesome. So make sure to go see her.
Thank you, everyone. Bye.